Okay, so let's talk a little bit about boundary conditions here. So here we have an incoming wave, and it's coming in with two different boundary conditions. The top one is going to have at the end an antinode. So you see at the very end there, it's oscillating up and down with a maximum amplitude. Whereas the bottom wave, the end is at a node. So what physically would be causing a node to happen? Any ideas? If it's fixed, if you tied it there, it can't go anywhere, right? Now, the top one, let's think about the other extreme. Maybe it's a free end. So what would cause this to be happening? So this incoming wave is coming in at the boundary, and it's reflecting off of this surface. So the way that the wave reflects back is going to determine whether you're going to get an antinode or a node. Okay, so I have a cool applet here. Let me see if I can get this thing working. All right, hold on. I'm going to have to slam this over to your view. Okay. So now I have to mouse while I'm looking up here. Okay, so here what we have is, let me do this one first. Let's talk about our antinode end. Okay, from a free end would be this one. Okay, so here we have our incoming wave, and it's hitting some reflection boundary. We want to know what the heck is the wave reflecting back going to do. So if we want the wave reflecting back to give us a max, to have the possibility of having a maximum amplitude, we want those waves to add constructively. So that means that the wave that's going to be reflected off, and click this and I'll show our wave that's reflected, is going to be reflecting off, and there's going to be no phase change. What that's going to give us is an amplitude that looks something like this. Ooh. Okay. Now let's talk about the other case, where if we have a node at the end. So that's this other tab right here. Okay, here's our incoming wave. It's the exact same as the one with the antinode. But now let's imagine, what does the reflected wave have to do in order to guarantee we're always going to have a node at the end? Yeah, we're going to need destructive interference. We're going to need a phase change. So let's see. All right. So you can see that this wave bouncing off this blue wave always has a pi phase change. It looks like it was flipped around the x-axis here. And so therefore, at the boundary, right here, right where it's reflecting off, you can see that the amplitude of the income wave and of the reflected wave are always equal and opposite, so they're always going to add to 0. Okay, so let's check this applet and see if that works. Ooh. Okay, so now when do we get when does one thing happen versus the other? So let me try to get back over here to my slideshow. Aha. Okay. Any ideas when one would happen versus another? Well, we said that if you have a node, that's the equivalent of having like a tied end, right? So that's, you can think of it either as you tie it to like the cable, or you can think of if you were propagating it through and less extreme, maybe it was going from a really, really thin string to a big heavy rope. It would have a hard time. That big heavy rope might look like a node, might look like something that can't move. So basically, that's in the extreme case. In the less extreme case, anytime you're going from a string that has a lower density to one that has a higher density, the reflected wave is going to have a phase shift of pi. Conversely, if you're going from a string that has a density to one that has a lower density, it's going to have no phase shift. Okay. Okay, and mathematically, what that looks like here. So it's one with the antinode. So this is our reflected wave. So if you take a wave, and I want to reflect it around x equals 0. I'm just going to draw what that would look like if it kept going. So back from the good old days of learning functions and things, if you want to reflect it about boundary, you take your function of x and you let it go to a function of minus x. And that will give you this wave. If I'm going to draw the mirror reflection of this dotted one over here, I'll give you something that looks like this. So this would be your wave reflecting back that has no phase change. Just to be clear, this wave isn't really here. We're just drawing to see what its reflected counterpart would look like. So that's what we're doing up here. And conversely, down here, we have, so basically pulled out the negative sign, and what we end up getting is a wave that's traveling back towards us, but it looks like A is negative. And when you go through the trig identities, which I won't go through again this week, you'll find that you end up with something where at x equals 0, it's a cosine function, so it's always an antinode. Conversely, if you, for the node version, if you do the reflection about x equals 0, and you give it this negative sign, this phase change to begin with, we end up with this a sine kx plus omega t. If you combine these two waves, you end up with something that looks like 2a sine of kx times cosine omega t. So at x equals 0, that will always be 0, so I'll give you a note. Okay, so I think that for most of these problems, the easiest thing to do is to do this pictorially. So if we want to know how to find what a resonance condition is, and by a resonance condition, I mean finding a resonance is when in a given length of string, you can fit an even number of half wavelengths for the waves that we're talking about. So what we can do is we can draw this, and we can find a condition between the strings. So what we can do is we can draw a length L. What we can do is on this string, we can determine what are our boundary conditions. Are we going to have nodes or antinodes at the end? We can draw in, so if we have, say, something that has nodes at either end, we can draw in what the string might look like, and we can find a relationship between the length of the string and the number of antinodes. So for this one, it looks like in the given length L, it looks like we can fit 3 lambda over 2s. So in general, if we want to fit n antinodes, we would fit n, 1, 2, 3, half wavelengths. This right here would tell us a relationship between lambda, n, and the length of the string. Then if we wanted to somehow relate that to the frequency of the string, we would use our equation that the velocity of the wave equals the wavelength times the frequency of the wave. And based on that, we could find a relationship between frequency and wavelength.